Hello, everybody. We're going to continue our discussion of continuous random variables with a discussion of the normal distribution. The ever important, extremely important normal distribution plays a huge role in statistics for a number of reasons. But let's get to it. Important, continuous probability distribution that we use in statistics a lot. Okay. Many variables have something that's approximately normal. The normal distribution, as we'll see in a minute, is a precise mathematical function that doesn't fit things exactly in the real world, but it fits them approximately well very, very often. And there are actual mathematical reasons for that, something we'll talk about a little bit later on, but also just something we happen to see in the real world a lot in data when we're taking a sample and getting some measurements and plotting a histogram, say, we often see this, bell sort of shaped curve. This type of idea, which we'll see in a minute, is this bell-shaped curve is kind of like the normal distribution, but the normal distribution is something very precise, and we'll talk about that. Okay, so and as I said, a lot of the times when we are taking a sample and plotting things out, it is pretty common to have something that's roughly normal. But also, in addition to that, a lot of statistical theory has built up around the normal distribution, partially because we see things that have approximately a normal distribution a lot, but also because a normal distribution theory works quite well, and the mathematics behind certain procedures work out really, really nicely, and so it's something that's been worked on a lot and well established with some very nice, clean mathematical results for us. Okay, so the normal distribution, and one thing I have not mentioned, so I'll mention now, it is very commonly referred to as the Gaussian distribution in honor of Carl Friedrich Gauss, but I'm going to just stick with normal. But you do see Gaussian a lot. Okay, so what I've got plotted out here, just to give us a little idea, this is a normal distribution. As we'll see, the normal distribution has two parameters. Its mean, right? We've got this mean of 162, and here is standard deviation. So 162 centimeters and 7 standard deviations. That's this normal distribution down here, which is approximately the distribution of the height of a randomly selected adult American female. So it looks quite a bit like this. And we'll see, we've talked about this with continuous distributions already. This is our probability density function, and I've discussed the meaning of that in another video and talked about that a fair bit. But it is not a probability itself. It helps us get probabilities because probabilities are areas under this probability density function. So we see something like this, the height in centimeters. This distribution is saying, well, getting heights near the mean of 162 is fairly likely, and getting heights, 150 when we're starting to get a little bit farther away, and 150 or into the 170s, a little less likely, and it just trails off from there, becoming less and less likely the farther out we go. And so we just tend to see this type of thing very frequently in all sorts of different data sets in the real world. Okay, so we have a very specific mathematical formulation, though. We have a probability density function, right? The specific probability density function of our normal distribution. And it is this thing. And first of all, if a random variable x has a normal distribution, then it can take on any finite value. And depending on the value of the parameters, that might be restricted to a certain region. So technically, there's going to be non-zero area of little intervals no matter how far we go out, but that area can be very, very, very small. So if we go back up here to the heights, say, you might say, well, if it can take on any value on the real line, how are we going to use it to model height? Well, the curve, when we start getting farther and farther out, many standard deviations out, this curve starts getting really, really close to zero. The probability density function gets very, very close to zero when we start getting really far out. So there's just not a lot of area at all left in the out far in the tails. Okay, so our probability density function is this precise mathematical function here. There's two parameters of the distribution. Our normal distribution is of this form, and then there's two bits of information we need to know to be able to plot the curve. And one of them is mu. Up here, this mu, which is the mean, has the same meaning as we've been discussing so far. That's mu, the true mean of the random variable x. And we have sigma, which is the standard deviation of the random variable x, or of this distribution. And we also have variance if we wanted, right? That's the standard deviation if we have it like that. And if we square it, we get the variance. And so you might say this distribution has two parameters, which it does, the mean and the standard deviation, or we could say the mean and the variance, either way, because the variance is just the square of the standard deviation. The mean can be any finite value. It's got to be finite, but it can be any finite value. It doesn't have to be positive or in any other interval, so it can go anywhere from any finite value on the real line. So it can take on negative values, positive values. It could be any finite value. Sigma, though, it's a standard deviation, and it's got to be positive. It's got to be a positive finite value in order for us to have a normal distribution. So that's the restrictions on that. Mu can be any finite value. Sigma, standard deviation, any positive finite value. We don't allow it to be 0 because if it was 0, it wouldn't have a normal distribution. 0, there's no variability, and it's not a normal distribution, right? In addition to this 0 in the denominator here, so we don't allow the 0 part for the sigma. Mu, the mean, can be 0, and quite often is. Okay, so we're going to look at the meaning of a variety of these things, try and get an idea for what those parameters mean. And first of all, mu, we can see here, very important to recognize, and visually it looks like this, but it is true in a mathematical sense, that this probability density function is symmetric about mu. So it's a symmetric about the mean. And mu is right here in the middle. It is the mean of the distribution, but it's also the median because it splits this distribution such that there's half the area to the left and half the area to the right. So mu, we usually think of it as the mean, but it's also the median. We think of it as the median quite often as well. Now, what about that standard deviation? Well, if we go over here, if we start off with have our normal distribution and we have the mean, and we go one standard deviation less than the mean to one standard deviation above the mean, that contains about 68% of the area. You might say, where'd that number come from? Well, we need to use software to get it, and we're going to show that. I'm going to show that. We'll take a quick look at that. I got it from software, but that is the area under the curve to 3 decimal places. Now, you might remember, maybe you remember, the empirical rule. And the empirical rule way back when, we said, well, for mound-shaped distributions, about 68% of the observations fall within one standard deviation of the mean. We said that back in sample data. That's all based on the normal distribution, what we're talking about now. And this normal distribution, if we jam it through mathematical formulations and software, we get this, that it is about 68% of the area from one standard deviation less than the mean to one standard deviation above. And we'll look at the corresponding things from the empirical rule for 2 and 3 standard deviations in a moment. Just one quick note for those more mathematically inclined. One standard deviation out away from the mean, these points, it's also where it turns from concave down to concave up, right? That's that point of inflection there where we change from concave down to concave up. That's not really super necessary to know unless you're looking at things from a very mathematical perspective, but also not too shocking from the visual there. And same idea if we go over here to 2 standard deviations. Well, if you remember, the empirical rule told us that about 95% of the observations will fall within 2 standard deviations of the mean if we're talking about a mound-shaped distribution. And we've got this normal distribution. Well, that's what we get. If we go to 3 decimal places, the area between 0.95, let me rephrase that. For 2 standard deviations below the mean to 2 standard deviations above the mean captures about 95% of the area, and 3 standard deviations below the mean to 3 standard deviations above the mean captures 0.997 of the area. And we know the area under the entire curve is 1, right? Because it's a continuous probability distribution. So hopefully this gives us a little bit of a feel for what the standard deviation is. When we push out 3 standard deviations above the mean to 3 standard deviations below, we're capturing, almost all of the area in a sense. There's a meaningful little bit outside of that, but when we're starting to go farther and farther out, we're capturing almost all of that area. Okay, so another little visual here for us in terms of what the standard deviation means. 2 normal distributions with the same mean, and the red dashed curve has a standard deviation that is twice as big as the blue solid curve. And so what we see when we have a greater standard deviation, and there's more variability, we have this greater spread here, a lower peak, and more area out in the tails. So hopefully that gives you a little bit of an idea of what mu actually means and what sigma actually means in terms of the curve. But these do just appear in our precise mathematical function here. And if we look closely, we can tell certain things like, oh, this isn't too surprising. Or at least we can tell even by looking at this that, well, the only place x appears is right here. And so we're going x minus mu squared. So the fact that there's symmetry about mu, well, that's coming from that little part there. This quantity is the same value if this x is 2 bigger than mu, or if it's 2 less than mu, say, because we're squaring that away. So it's the distance from the mean that matters in terms of the probability density function. Okay, so we have this, so there's an infinity of normal distributions with all sorts of means and all sorts of standard deviations. And we have a special one, though, that we talk about a lot, and that is the standard normal distribution. And by definition, the standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. That is what standard normal distribution means. It's a normal distribution, mean 0, standard deviation 1, or equivalently, variance 1, because you square 1, you get 1. So standard deviation 1, variance 1, that's a standard normal distribution if the parameters equal that. And we often let Z represent random variables that have the standard normal distribution. So very, very often if we have something that's standard normal, we let it be Z, and so we'd say Z has the standard normal distribution, mean 0, variance 1. So let's see what that looks like. This is the probability density function. Again, this is our probability density function of our normal distribution. We get this nice bell-shaped curve, and it is the standard normal in this case, and so the mean is 0. So the standard normal distribution is symmetric about 0. Standard normal distribution is symmetric about 0. That's hopefully pretty easy to remember and think of going forward. And if we think back to, well, the empirical rule and the plots that I showed you there, we're going to have, well, about 95% of the area between -2 and 2. Almost all of it, or 0.997 between -3 and 3. And when we start going farther and farther out, we're capturing more and more of the area and getting nearer and nearer 1. So our probability density function looks like that. And we're going to be using this to model real-world variables, and we're going to need probabilities and percentiles from it. So we'll take a look at a couple of things in a moment. But down here is our CDF. Our cumulative distribution function. If you remember this, what the CDF is the probability the random variable, well, in this case, we're talking about a random variable Z, so it'd be the probability that your random variable Z takes on a value less than or equal to little z. I'm just going to put a cross through the little z, representing the little z. So your cumulative distribution function is, Well, one way to think of it is it's the area under the probability density function, the area to the left under the probability density function, but it's also the probability your random variable takes on a value less than or equal to that input value. So for instance, if we looked at this at 0, we know this the standard normal distribution is symmetric about 0. That's not a very straight line, but we're just going to have to go with it. Which symmetric about 0, so there's 0.5 of the area to the left of 0 and 0.5 of the area to the right of 0. And if we went here for our cumulative distribution function, right, that's exactly what that is. At 0, it's going to be 0.5, right? And starts out here far in the left tail near 0, and then when we start getting here, it starts accumulating more and more area, and when we get to 0, it's got half the area to the left, and then when we get up over here, we're gonna, by this point, we've got, you know, almost all of the area, and as we go farther and farther out, it's getting closer and closer and closer to 1. So software has this function built in, and it's going to give us areas, right? The area to the left. That's what this cumulative distribution function is, and we need to find these to answer some questions of interest for us. And so let's just do a couple. I have another video where I go through a lot of these things, but let's just do a couple of quick ones here if we're doing these sorts of things. So we need to find areas, because areas are probabilities, and we're going to be using this in things like statistical inference, and we're going to need to find probabilities, or just maybe not even statistical inference. We just want to find probabilities of certain things. So let's say I want to know the probability that the random variable z takes on a value less than or equal to minus 1.38. I'm just going to do a couple of these. Like I said, I have another video where I walk through a bunch, and you have to do some yourself. So if we want this is the probability density function. I'm just scratching it out here, and we don't have to get it just right, but I'm just drawing a less pretty version of this. 0 is in the center, minus 1.38 is over here somewhere. We don't have to get it right on the money, we just put it over here. But the probability that your random variable z takes on a value less than or equal to minus 1.38 is the area under the curve to the left of that. So that's what that is. That area to the left, that's what that is, right there. Okay, now we don't have a closed form solution for that. We don't have a little formula we can put stuff in and get that. That's not how it works. So this curve has to be integrated to find that area, but it also has to be integrated numerically. The integral doesn't end up with a nice closed form solution, so we need to use software. So function is built in to all sorts of software to find areas under the standard normal curve, and R has the function p norm. So p norm gives us the area to the left of the input value. So if we want to look this up in R, and if we go to software, if we punch all of that in, that we'll see that is 0.0838 to 4 decimal places. That's what we get. Now, if you're not using software, we do have statistical tables that just write down the values from software in table form, but I'm not using tables anymore. So we're just going to go with the software route, and in Excel or whatever else would have it, but we're using R. So the probability the random variable z takes on a value less than or equal to minus 1.38 is this quantity. Couple of points to note. There is symmetry about 0, so we could quickly, if we wanted to, say, hey, right here then, if it's at 1.38, if I want that one, then I can say, well, I figured this out. That is the same as that. That area there is the probability the random variable z takes on a value bigger than or equal to 1.38. And that's the same because of the symmetry about 0. So we would get that. And that's something we might want to deal with. And so then the other side of things, if we want an area to the right of our value, well, depends on what we're doing. We have the symmetry argument here, but let's say if I wanted to work with that still, and I wanted to know the probability the random variable z took on a value bigger than minus 1.38, I need to recognize that the area under the entire curve is 1, And so this is just going to be this whole area out here, right? This area to the right of my minus 1.38, and that is going to be 1 minus this one. So that's going to be 1 minus 0.0838, and that's going to be 0.9162, right? Okay, to 4 decimal places anyway. So I'm not going to do a whole lot of these because I have another video where I go through it, and you're going to have to work through some of that on your own, but I do have another video completely dedicated to doing all sorts of problems like this. We'll do a couple more in a different setting in a minute or two. But the other thing we might want to do, is find like the inverse of a sort of notion. Rather than be given a z value and be asked for an area, I might want to find a z value that gives us a certain area. So let's say I wanted to know what is the 80th percentile of the standard normal distribution. Let's say I want the 80th percentile of the standard normal distribution. So I have to recognize that, first of all, I get my standard normal distribution. It'll look something like that. Zeros here. The 80th percentile is the value of the variable that has an area to the left of 0.8. So there is some value out here. The area to the left of 0 is 0.5, so the 80th percentile has to be out here somewhere. Some value out here, which is the 80th percentile right here, that gives us an area to the left of 0.80. Now, there's no closed form solution for this. We have to use software. And R has the inverse function of P norm. And the inverse function of P norm is Q norm. So Q norm takes as an input the area to the left and gives you the value that makes that happen. And so if we were to do this in R, if we put in our Q norm and the 0.8, we get that the answer it gives us is 0.8416. Or in other words, 0.8416 is the 80th percentile of the standard normal distribution. And one thing to note when we're working with R here, that people want to use the standard normal distribution a lot. That's the most common one we use. So R has as a default, if you just put P norm or Q norm and the value, and you don't put in a mean or a standard deviation, R will assume they're 0 and 1, a mean of 0 and a standard deviation of 1. Now, it may very well not be the case, right? I'm just saying, if you're using a standard normal distribution, if you're working with that and you want to use find areas under your standard normal curve in R, then you can use P norm, your value, and then put in 0 or 1, or you can just leave out the 0 or 1. And as we'll see in a minute, when we're talking about different distributions, not the standard normal, other types of normal, different mean, different standard deviation, we'll have to make sure we input our mean and standard deviation in there. Now, so we worked this out, 0.8416 is the 80th percentile. So how about, let's say if we did something pretty quickly here, the 20th percentile. What's the 20th percentile? Okay, it doesn't really look very good, but that says 20th percentile. We should be able to do that really fast, right? Sure, you can throw it in R, or symmetric, about 0. So there's 0.2 of the area out to the left, to the right of 0.8416, which means there is 0.2 of the area to the left of minus 0.8416 by the symmetry about 0 argument, which means minus 0.8416 is the 20th percentile of the standard normal distribution. Okay, so you got to get comfortable with that, get that down. And we'll need this for other distributions. Easy adjustment once we got that down. Standardizing normally distributed random variables. So if we have the random variable x being normally distributed with mean, mu, and standard deviation sigma, and our notation for that, x is distributed normally with a mean of mu, and the second term is the variance. That's what we've been we're going to do for our normal distribution. Some sources have just the standard deviation there. This isn't universal notation, but it's common notation, and it's the one I'm using. Random variable x is normally distributed, mean mu, and variance sigma squared. That second term is going to be our variance. So that's our notation. But one thing, and this is an important thing, we can convert x here. If x is normally distributed with any mean, any standard deviation, we can convert it to something having the standard normal distribution. And it's just a basic linear transformation. We're going to say this z. Why I'm going to call this quantity z, I'm putting that down. I'm going to have a quantity over here. And I know the punchline is that this thing that we're going to write down has the standard normal distribution. So I'll call it z here. But if we start with that random variable x and we subtract off the mean, if we just did this x minus mu, this x minus mu quantity would have a mean of 0. X has a mean of mu. If you had a quantity x minus mu, well, that's going to have a mean of 0. And if we divide by the standard deviation, that's forcing this quantity to have a standard deviation of 1. So forgetting about normality for a second, if we have some random variable x and we subtract its mean and we divide by its standard deviation, then that random variable that you just created will have a mean of 0 and a standard deviation of 1. But if in addition x is normally distributed, then z is going to be normally distributed because we're not doing anything to change the shape. This is a linear transformation. We're subtracting a constant. We're dividing by a constant. That does not change the shape, so we're still normal. And we would have a mean of 0 and a standard deviation of 1. And so if we do that under those conditions, then this quantity, then z is distributed normally with a mean 0 and a variance of 1. So we can standardize and get this standard normal random variable from any normal random variable. And it's perhaps tough to discuss why that's an important and meaningful thing for us, but it comes up a lot. Just that notion, we want one formula for things. We want to be able to have a test statistic and hypothesis testing, be able to just have one thing that we can write down and use all the time, and have a certain distribution under certain conditions, things like that. So we liked having this standard type of a setting, and we can achieve that for when we're starting with any normally distributed random variable. Okay, so now what might we do here? Why might we care? So this example, we've got this study investigating the amount of riboflavin in grade A large eggs, and they found that it's approximately normally distributed with a mean of 0.25 milligrams and a standard deviation of 0.02 milligrams. So if we let the X represent the amount of riboflavin in a randomly selected grade A large egg, then X is going to be normally distributed approximately with a mean of 0.25, right? That's mu. As I'm saying, we're going to pretend that we know mu here, so that looks pretty ugly. Let's try that again. So in reality, we wouldn't know it, right? We're not going to know it for sure. Right? But we are pretending we know it based on some information from a study, this sort of idea, in order to get some of the foundational aspects of the normal distribution down. Now, big picture-wise, we're going to be later on estimating mu in different settings. We're going to be using what we learn in order to estimate mu and do some statistical inference and that sort of thing. But for now, we're going to pretend that we know it. But this is based on real information, and roughly close to the truth. So under these conditions, X is approximately normally distributed with a mean of 0.25, and the variance, the sigma, is the standard deviation here of 0.02, and the variance would be 0.02 squared. So I'm just going to leave it like that. I'm going to leave it as 0.02 squared rather than actually square it out, because in practice, in our formulas, we're going to be taking the square root of that anyway. But saying X is normally distributed, mean 0.25 milligrams, and a variance of 0.02 squared. Okay, now why do we care about this? We are going to randomly select a grade A large egg, and we want to know the probability it has less than 0.22 milligrams of riboflavin. And remember up top, we said, all right, X is approximately normally distributed with the mean of 0.25 and a variance of 0.02 squared, or in other words, the mean was 0.25 milligrams, or I'm going to put this over here. The mean was 0.25 milligrams, and the standard deviation is 0.02. So what's the probability this randomly selected egg has less than 0.22 milligrams of riboflavin? What's the best way to do that? We just throw it directly into software. 0.22. What do we want, right? That probability. So we want the probability that x takes on a value less than 0.22. What is that? That's the area under the curve to the left of 0.22. So here's 0.22. Our normal distribution with the mean of 0.25, right? Here's 0.25 in the middle, standard deviation of 0.02. This is what we want. We want this. That's what that is. And we have to go to software to get it. But R will find this for us, or other software. We just need to use the appropriate function. So if we put this into R, we say, hey R, let's get the area to the left of 0.22. So we 0.22, area to the left of 0.22, under a normal curve, but you got to tell it the mean, and R wants the standard deviation for the second one. What I'm giving you up here is mathematical notation. That doesn't necessarily sync up with every bit of software in the world. R wants the standard deviation as the second term. So we'd put in our P norm, 0.22, and 0.25 for the mean, and 0.02 for the standard deviation. And we get, overall, 0.0668. Okay, we're done. We answered the question. But if we don't have access to software, that's the easiest way. If you're asked that in the real world, you just answer it like that. You put it into software, you get your answer. Okay? But if we don't have access to software, if we're using a table, or if we wanted to standardize and for illustrative purposes, let's say we did this through the standard normal way. If we're using a table, then we would, rather than software, we would have to standardize this. So what we want is the probability the random variable x takes on a value less than 0.22. That's what we wanted. But the thing is, we can convert this into something that has the standard normal distribution, because we can say, hey, I could do this. Humor me for a moment. I could subtract the mean and divide by the standard deviation on both sides. I didn't do anything there. And the standard deviation's a positive quantity, so it doesn't flip the sign or anything like that, or nothing to worry about, and it's non-zero, and nothing like that. So this works fine. Just both sides we subtracted a constant divided by a positive constant. Everything's cool. Okay, but wait, this quantity is your random variable z. So this is the probability that z, that's what z is, x minus mu over sigma. If we do that, we get something that has a standard normal distribution, if x is normal to begin with. And so then we go less than this quantity. I'm just going to put the value of the mean in here now, 0.22 minus 0.25 over sigma, which is 0.02. Okay, and what's that? That's the probability the random variable z takes on a value less than minus 1.5. 0.22 is 1.5 standard deviations less than the mean. And so we go out here, we say, all right, 1.5 is somewhere out here, right? And we've got this, and we have, or minus 1.5 is there, and we want to find this area out here, right? That's what this is going to be. And if we put this into R, if we go our P norm minus 1.5, 0, and 1, we get, lo and behold, 0.0668. So we get the same value. And what we could have done, like this is our standard normal curve down here, right? I plotted out my standard normal curve. And when we're faced with a question like this, we just put it in the way we did it up top and get our answer. If we have access to software, that's what we do. But we can also do this by doing this linear transformation, expressing it in terms of a standard normal random variable, and we'd have to do that if we were using a table rather than software. So that's how we can find these areas that go straight into R, or standardize at first, depending on what you have access to. But if you have access to software, don't bother going this route. Just put the values in right up top and get your answer right away. The other way here, let's say we wanted the 90th percentile of riboflavin content for grade A large eggs. Well, the 90th percentile is the value of the riboflavin here that gives us an area to the left of 0.90. By our definition of a percentile, this is the 90th percentile. We could throw this straight into R and get our answer. Okay, straight into R and get our answer. So remember, of course, that mu is 0.25 here, 0.25, and the standard deviation is 0.02, and R has a function that'll do this for us. R has a Q norm function that takes as an input the area to the left and gives you the value that makes that happen. So we would just go to R and put in Q norm and the area to the left, 0.90, and our mean and standard deviation, and we get our answer here. And what that works out to with R tells us that's 0.2756 to 4 decimal places. I got that, right? That's the 90th percentile of the amount of riboflavin in grade A large eggs. At least approximately so, right? This is the riboflavin has approximately that distribution, so this is approximately our 90th percentile. Now, if we didn't have access to software and we couldn't just go straight to it and just say, hey, R, what's the damn value? We have to convert it. We have to go about this a little bit differently. And remember, we have this notion that our Z is equal to X minus mu over sigma. And then if we rework this, right, that implies if we rework this, sigma is up here, right, that our X is equal to mu plus sigma times Z. So what we're going to do if we were forced to, and we're just drawing the parallels here, right, between these things too. It's not just if we had to use a table. It's the notion to see what's happening here in this linear transformation, which we'll use frequently. It just comes up a lot. What we'd do is we'd find the 90th percentile of our standard normal distribution. If we find the 90th percentile of our standard normal distribution, that's the value that gives us an area to the left of 0.9. We want this value, the value that gives us an area to the left of 0.9. And again, we'd use that Q norm, right? We use our Q norm. And if we did that, put in Q norm 0.9, R would tell us that the 90th percentile of the standard normal distribution to 5 decimal places is 1.28155. And then if we substitute this in, we want our X value, but we just put this in up here. So the 90th percentile of this, the riboflavin, not of our standard normal distribution, but of the riboflavin, say, okay, well, that's going to be our X equals, well, our mu, which is 0.25, sigma, which is 0.02, and then times our 90th percentile of the standard normal distribution. And that, other than a little rounding error that we might get sometimes, is equal to this thing up here that we got from R in the first place. But it's useful to see how these things work together, and it's useful to see what's happening when we do a linear transformation like that. And we do have later in, like I said, in hypothesis testing, we have a Z test statistic that's of this form, and we have this transformation like this expressed of this form, so that we have this coming up for us a lot. Just quick little side note. Remember again that the distribution is symmetric about 0. So if I were to ask something here like what's the 10th percentile of the standard normal distribution, well, that's a pretty fast one. That would just be, if we wanted the 10th percentile, that's the value out here with 0.10 to the left. There's 0.10 to the right of 1.28155. So this value would have to be minus 1.28155. That's just a little side note, just bringing in again that's very important to know a couple of things, that our normal distribution is symmetric about mu, and the standard normal distribution has a mean of 0, so the standard normal distribution is symmetric about 0. The area under the entire curve is 1, And then when we've got our P norm and our Q norm like that, we can just work with those to get exactly what we need in different settings. So do some of those, get familiar with that. I have other videos where I walk through all of that. You want to be familiar with this. And when you get this down, it's going to be easy for other distributions because it's the exact same format. All right, talk to you later.